In your previous chemistry subjects, you have encountered the different elements represented in the periodic table of elements and how these pure forms of matter interact with each other to comprise matter. In this particular chapter, the history of the creation of such element will be discussed and how the field of chemistry emerges a branch of science. At the end of this particular lesson, you should be able to provide evidence and explain the formation of both light and heavy elements and write and balance nuclear reaction involved in the synthesis of new elements. So let's have a short review of the atomic structure. The Greek philosophers who lived during the period of 600 to 200 BCE were the first people on record to speculate about basic substance or substances that make up matter. In the 4th century, Aristotle developed the idea that all matter on Earth is composed of four different elements. That would be earth, water, fire, and air. Everything around us is made up of atoms. Atom is defined as the smallest particle of an element that retains its physical properties. All atoms are made up of nucleus and electrons. At the center of the atom is the nucleus, which is composed of both protons and neutrons, collectively known as nucleons. The nucleons, or the nucleus rather, is orbited by the electrons. After the postulation of Dalton's atomic theory, experiments and scientific inferences allowed to conceptualize the structure of the atom and the properties of component particles. Recall that nucleus contains both protons and neutrons, which define the atomic mass of a certain atom. Protons are positively charged and it would define the atomic number. On the other hand, the neutrons would be electrically neutral and that the electrons are negatively charged. Existing concepts in space science suggest that Big Bang theory proposes that our universe was born from a very hot and highly dense single point in space rather than simply being a huge explosion. So for this particular section, we will look into Big Bang theory, stellar formation and evolution, and lastly stellar explosion. One of the pieces of evidence that our universe is continuously expanding is observed in redshifts of celestial bodies, particularly the stars and their large assemblies called galaxies. The concept of redshifts were described by Edwin Hubble in 1929. In this particular context, as the distance of the galaxies approaches the Earth, there is an increased space between the Earth and the galaxy, which leads to wavelengths being stretched. Edwin Hubble discovered that the galaxy's velocity is proportional to its distance. Therefore, galaxies that are twice as far from us would move twice as fast. Another consequence that the universe is expanding in every direction. This observation means that it has taken every galaxy the same amount of time to move from a common starting point to its current position. Since then, the Big Bang since the Big Bang rather, the universe has been continuously expanding. Thus, there has been more distance between clusters of galaxies. After the second Big Bang, the temperature of the universe was estimated to be around 10 billion Kelvin, which dropped 1 billion Kelvin after 100 seconds, and now the current temperature of our universe is 2.725 Kelvin. The formation of elements occurred about 380,000 years after the Big Bang during a phase called recombination. The light elements such as hydrogen and helium were the first one formed. As the universe cools, down further, heavier elements are created. This explains why hydrogen, being the lightest element, is also the most abundant among the stars. As the universe cooled, neutrons either decompose to protons or electrons or combine with the proton to produce another isotope of hydrogen known as deuterium. So during the first 3 minutes of the Big Bang, deuterium combined to generate helium and trace amount of lithium. And the heavier elements were formed from the fusion of lighter elements. And this process is known to be nucleosynthesis. So, what happens exactly during stellar formation and evolution? Let's watch the video.
Stars form in nebulae, which are large clouds of gas, mainly hydrogen, and some dust, heavier elements. These clouds are huge, and the only force acting on the particles of the nebula is gravity. Gravity slowly pulls the gas and dust together into huge rotating balls. As particles are pulled together, they are accelerated faster and faster. Gravitational potential energy is being converted into kinetic energy. These balls of heated gas and dust are called protostars. If these balls of collapsing gas are big enough, particles in the core will be packed close together and moving fast enough for hydrogen nuclei to be squashed together to make helium nuclei. Nuclear fusion has begun releasing huge amounts of energy. A star is born. In a star, there are two sets of battling forces. Gravitational forces that form the star and continue to try to collapse the star, driving nuclear fusion, and thermal forces trying to make the star expand. There's a dynamic equilibrium as these forces battle it out, and slowly the star changes. In the case of an average star, like our Sun, fusion is turning mass into energy. The radiating star is losing mass, the gravitational forces are weakening, and the thermal forces are slowly winning, causing the star to expand. As a star expands, it is cooling. These larger, cooler stars are called red giants. Red because they're cooler. Giants because they're very large. As our sun turns into a red giant, it will engulf the innermost planets of our solar system, including Earth. The expansion of a red giant causes the star to cool. The thermal forces are weakening, and sooner or later the gravitational forces will again win. The core of red giant collapses into a small white dwarf. White because it is hotter. Dwarf because it is a small star. The outer part of the red giant remains as a shell of gas. It is thought that white dwarfs cool into black dwarfs. However, this is such a long process that it hasn't happened yet in the universe. Now, in the other case, in the case of a massive star, much heavier than our sun, the larger gravitational forces are driving nuclear fusion at such a high rate that the star is blue, much hotter. But it is using up its hydrogen more quickly. Again, thermal forces are causing the star to expand. The expanding massive star cools, becoming a red supergiant. The expansion of a red supergiant causes the star to cool. The thermal forces are weakening, and in this case, sooner rather than later, the gravitational forces again win. The core of red supergiant takes only a few days to collapse, radiating vast amounts of energy in an event called supernova. A supernova, for a short of time, can be brighter than an entire galaxy of stars. The outer shell is pushed into a deep space by the supernova. The core collapses into a neutron star, or, if massive enough, even a black hole.
universe continuously expanded for several years, and clouds of hydrogen and helium gases condensed to form the stars, so including the sun. Over millions of years, the stars made of hydrogen become hotter and denser. And during the stellar evolution, nuclear reactions continued, which produced heavier elements than lithium. And the light elements combined to form carbon, neon, oxygen, silicon, and iron. During the stellar explosion, as the red giant exhausted the nuclear fuel of light elements, its core started to collapse, and that eventually led to the explosion of the stars. This violet explosion is known to be the supernova. It produces a huge amount of nuclear energy and formed other elements heavier than iron. What we must remember is that a star is in balance of two opposite forces. The star's gravity tries to squeeze the star into its smallest, tightest ball as possible. But the nuclear fuel burning in the star's core creates strong outward pressure, and this outward pressure resists the inward squeeze of gravity. What you must remember is that when a massive star runs out of fuel, it cools off, and this will cause the pressure to drop. And gravity would definitely win out, and the star would suddenly collapse. Since we have an understanding of what or of how different elements were formed, the next lecture will now focus on the element itself. So I will be ending my presentation at this point, and hopefully you will watch my next lecture.